Yes, sir.
Yeah, thank you. So here, suppose already when we solved this Fermi second unit, so band gaps, whatever we say, it's like a parabolic. Generally, it's a parabolic shape they will have. Okay, here also they will have a parabolic. Like this is valence band, and here a conduction band. Okay, so here we are drawing EK or E energy versus wave vector. K means wave vector, or you can say P also. P is the here crystal momentum. Suppose here K is the wave vector, and P is the crystal momentum. It's not a normal momentum because we are discussing particle or electron motion in a crystal. That's why suppose light is propagating in a space that is different velocity, that is having a different velocity, and suppose electron moving in a crystal or any semiconductor that is having some different velocity. That's why here we are calling crystal momentum like effective mass of electron. Effective mass, why we are calling effective mass? Because there is a some external forces act on these particular electrons. Okay, that's why the mass of the electron or mass of the hole is changing. That's why we are calling effective mass. Okay, here also we are drawing. First, to understand the direct and indirect band gap, we have to draw EK diagram. So along the y-axis it is the energy, along the x-axis it's we are taking K or P, whatever you can take. Okay, this same will indicate same meaning. Okay, here energy and the y-axis energy. So in this semiconductor we are discussing direct band gap. Okay, this is direct. Here electrons, suppose here free electrons are there in the conduction band, here free holes are there in the valence band. Okay, so free electrons and free holes. After this lifetime, electrons jump into the valence band and recombine with holes. Recombine with holes. This is direct recombination process. In this process, what is happened? Here photon will be emitted. Okay, excess energy, whatever excess energy or loss, whatever electron lost in this process, or some energy this will last. Okay, this loss of energy emit in the form of photon or excess energy, whatever during recombination excess energy emits in the form of photon. Okay, this is the direct recombination and photons are emitting. And most important thing is here, so here recombination takes place via, see, minimum of the conduction band to maximum of the valence band. Okay, we are discussing here minimum of the EC. This is EC or conduction band. You can say this minimum energy we are calling EC, right? Maximum energy EV. So here we have to say maximum energy of valence band and minimum energy of the conduction band. This will be like in a same. Suppose here P1. Suppose here P1 P2 or P1 P2, whatever you take. So here P2 P1 is equal to P2, right? P1 is equal to P1. P1 is equal to P2. That means after transaction, after transition, you can say suppose electron is making transition from conduction band to valence band, but same momentum at the same k vector where this transition taking place. So at the, suppose if you take electron, the P2 is equal and P1. So these are on same line. Suppose here same value. Suppose here, suppose if you take Px value. So at the Px value, these P1 and P2 are coinciding. That means here momentum is conserving. What is that? Crystal momentum is conserving. Okay, momentum is conserving. Okay, you can write conserving. Okay, momentum is conserving because delta P is zero. The difference between momentum of electron before and after transition, the momentum is equal. That means the change in momentum is zero. That means momentum is conserving. And also in this process, if momentum is conserving, E is equal to h nu. This is also before and after transition. This is also conserved. This is also conserved. So in this direct band gap semiconductor, the transitions takes place always minimum of the conduction band to maximum of the valence band at same k value or at same p value. So here after transition, before transition, there is no difference in the momentum of the electrons. That means delta P is 0. That is equal to P2 minus P1. Okay, delta P is equal to P2 minus P1. So that's why the momentum is conserving. Once the momentum is conserving, here also energy also conserving. Before and after, there is no involvement of any other lattice or any other things. Okay, so that's why here energy also conserved. Okay, so your main important points are energy and momentum is conserving, energy and crystal momentum is conserving, and so your transition before and after transition same. This diagram also important. Okay, this is radiative transition, and this is, you can write radiative transition, and photons will emit. Okay, these are the few important points. Okay, you have to draw this diagram and you have to write 1 2 3 these 3 points. Okay, then it is completed. Now we'll go to the indirect band gap semiconductor. So if you draw same thing ek diagram, suppose here examples you will first we'll see example here, mostly compound semiconductor like gallium arsenide or gallium phosphide. Okay, gallium phosphide, gallium arsenide, phosphide. Okay, these are some example for direct band gap semiconductor. Mostly compound semiconductors, compound semiconductors, second and fourth group, and third and fifth group, and also you can write fourth and sixth group. Okay, these are the some compound semiconductor. If you combine second group element and fourth group element, it will become a compound semiconductor. Okay, these are all mostly direct band gap semiconductor, right? Is it clear to you up to this direct band gap? Is it clear?
Yes, sir.
Okay, now I will go to the second indirect bandgap semiconductor. Okay, this is also same thing. We are drawing EK relation. Okay, energy versus crystal momentum or wave vector. This is all indicate wave vector or crystal momentum indicate electron momentum in a crystal. Okay, or whole momentum in a crystal. This is K or P. You can write whatever. Okay, here energy. Okay, here same thing. Valence band is we are drawing same thing. Okay, this is valence band and conduction band here. Okay, the transitions are like this. It is so here maxima minima, here minima to minima, or you can say it is, suppose this is here longest distance. Suppose if you take this path, it is longest distance. So this path is shortest distance, path 1 and path 2. So whatever, when you give some energy to these electrons, it will make two first step. Suppose here you have a steps. Okay, here you have a step. So if you want to go first, you will go to first step, right? You will not directly jump to the second step, because you have only whatever you have energy. First you will step 1, and after that step 2, and after that step 3. So if you have very sufficient energy, we can directly jump from ground step to third step. Okay, this will depend on energy. You will jump into different steps. Okay, if you have average energy or less than energy, very low energy, you will jump into first step only. If you have a little bit more energy, you will jump into second step. Okay, if you have very high energy, then you will jump on to the third step. Okay, here also this whatever path 1, this one is higher level. So electron prefer to always less energy state. Okay, so electron prefer path 2. Electron prefer path 2. In this case, what happened when make transitions here? When make transitions here, so just I will try again. So step path 1 it will not flipper, only path 2 will flipper. Okay, now instead of this way, we'll draw some other kind. Okay, then you will just a second please. So in this transitions, suppose we are drawing different way. Okay, this way. Okay. So now here two steps are involved. Okay, or to jump from electron from here to here. Okay, or to make transition from, suppose this is P1 and here P2, right? So to make transition from valence band to conduction band, this is conduction upper one. Here two steps are involved. One is electron transition, another lattice also involvement is there. Electron and lattice also involvement is there. So electron doesn't have energy. It will take some energy from lattice. Once this interact, some electron interacts with lattice, and they will get some energy, and it will jump into the conduction band. Here up to here energy is h nu, and here h cross k. H cross k. This is lattice energy. H cross k is the lattice energy. Generally electron energy having energy is h nu. So total energy is here h nu plus h cross k. H cross k is due to lattice interaction. H nu is the general energy of electron. Okay. Here energy is conserving before and after transition. The energy is conserving, but momentum is not conserving. Why? Because see, at position, if you take valence band, so here is the P1. Here is the P1. After making transition, the momentum is changing. After making the transition, the momentum is changing. The difference between before and after transition, the delta P, it is equal to P2 minus P1. P2 minus P1. The change in the crystal momentum is not equal to zero. Not equal to zero, because after transition, the electron is going to some other place. Electron is moving to some different place. First one, here in the first case in direct bandgap semiconductor, before and after, the momentum is changed. Momentum is same. For suppose in first figure, first diagram, the after and before transition, electron having same momentum, P1, P2, but P1 is equal to P2. But here in the second diagram, if you come to here, it is indirect transition. It is not coming directly. So here lattice interaction is there. Lattice means it is a systematic. If you take lattice, what is lattice mean by? Okay, it is a systematic arrangement of atoms. Okay, it is a systematic arrangement of atoms. Suppose like atoms are arranged very systematic manner. This is the lattice. Okay, electron, when lattice an electron enters it in this here, this electron make interaction with this lattice atoms, or it is interacting with the lattice means it is interacting atoms in the crystal. That is the meaning. Okay. So here before and after, the momentum of electron or wave vector of electron is different. Okay, that's why here delta P is not equal to 0. That P1 is different and P2 is different, or K1 is different and K2 is different. This kind of semiconductor, what we are calling indirect bandgap semiconductor, where here energy is conserving. In indirect bandgap semiconductor, energy, whatever energy is conserved. Okay, but momentum is not conserved. Momentum is not conserved. Okay, this is indirect bandgap semiconductor. Here what will interact? So when we studied indirect bandgap, in non-radiative recombination or indirect bandgap recombination, so there is lattice. When lattice interact, here phonons will be made. Phonon, okay, phonon. So here seeing when electron recover, here phonon will be emitted, because here electron is interacting with lattice. Okay, because of this lattice interaction, there is a heat is generating, or this heat we are calling phonon or mechanical wave. This is a mechanical wave. Okay. So in this process, mainly steps are energy is conserving before and after collision, but momentum is not conserved, because before and after transition, electron having different momentum. Different momentum. Okay, this is the difference between direct and indirect bandgap semiconductor. Okay, so how you will do this one means, suppose if you take absorption spectra, this is absorption coefficient and this is energy. So if it is direct band gap semiconductor, the curve is, it will come straight. Okay, it will come straight. Okay, this is direct. This is direct band gap semiconductor. Okay, suppose if it is not like this, if spectrum is like this, it's a slanted. So it is a indirect band gap semiconductor. Indirect. So making this, you can measure the absorption of any sample as a function of energy or as a function of wavelength or frequency. From there you plot the graph, and if curve is comes straight, it is a direct, and if it is not coming straight, it's like it will come as like this way, it is a indirect band gap. This is experimentally you can do it, but this is what we have studied just now. It is a theoretical way. Experimental also you can do different measurements. This is one of the measurement, measuring the absorption coefficient as a function of frequency or wavelength or energy, whatever you can take here. Okay, on the x-axis you can take wavelength or energy or frequency, but on the y-axis you measure the absorption. So absorption is, you can write this formula: I is equal to I0 e to the power of minus alpha d. Alpha d is the thickness of sample, and alpha is the absorption coefficient. You can write 1 by d, 1 by d ln of I by I0, I by I0. Okay, this way you can measure the absorption coefficient from experimentally, and you can plot it, and you can know which. Suppose I gave you two semiconductors. I will ask you which one is direct band gap and which one is indirect band gap. Theoretically, you cannot do with sample, right? So immediately you have to measure the experiment. UV measurement is there, UV visible measurement, UV visible. In that measurement, you put the sample and take the data, and you calculate alpha, and you will scan the spectra with respect to frequency or with respect to wave. Okay, chart the graph. If it is slight, it will come straight, it is direct. If it is slanted way, it will come, it is indirect band gap. This is experimentally you can proceed. Okay, so I think you understand, right? So in direct band gap, the photon will be emit excess energy, emit as a name, as a form of photon. So this will done when band to valence band and electron recombine with hole. Okay, here photon is emitting and energy momentum is conserved, because before and after transition the momentum is same for electron. So that is the direct band gap. In indirect band gap semiconductor, so here there is a involvement of lattice is there. So electron directly cannot jump into the conduction band. That's why it will take help from lattice. Okay. So here lattice energy also involved. Okay, lattice energy also involved. In this case, phonon will be emit. Okay, this is a heat or mechanical wave. So before and after transition, the momentum of electron is not same. It is a different. So that's why delta P is not equal to 0. That means momentum is not conserving. Only electron is conserving, and here phonon will be emits. So examples are, okay, examples are in this case like silicon is indirect band gap semiconductor, and germanium also indirect band gap semiconductor. Silicon germanium is indirect band gap semiconductors. Okay. So experimentally, you can perform the UV visible spectroscopy measurement. You measure the alpha, thickness of the sample, and this transmission I by I0 is equal to the transmission percentage. Okay, transmission, how much the sample is transmitted, how much light is transmitted through that sample, and you can know alpha, and you can plot the as a function of wavelength. Then if it is straight line, it is direct. If it is it's not straight line, it is indirect band gap semiconductor. Okay, examples are here silicon germanium for indirect band gap, and direct band gap gallium arsenide, gallium phosphide, gallium arsenide phosphide. Like is compound semiconductors are some example for direct band gap semiconductor. Okay, lattice means it is a system of atoms in a crystal, that is called lattice. Okay, lattice definition is systematic arrangement of atoms in a crystal. Okay, in a crystal or in a any semiconductor or any material. Okay, that is lattice means. Okay, up to now is it clear to you? Any doubts do you have?
Clear, sir.
Okay, thank you. So now we'll move to the LED. That is very, very important topic. Okay, what are suppose where you are using these LEDs. Okay, LED means emitting diode, light emitting diodes. Okay. Emitting diode.